Good afternoon. In today's session, we are supposed to study about the back EMF in DC motor and torque. We are supposed to study how we are supposed to derive the equation for the torque. So here, what we are saying, we are now studying about the DC machine. There are two types of DC machines, DC motor or a DC generator. So we can see DC machine as an electromechanical energy converter, because if you see, they are using the electrical energy or they are inducing the electrical energy. It means what? If there is a DC motor at that time, it will use electrical energy and it will convert that energy in the form of mechanical. And DC motor is doing electrical to mechanical converter. But if you see about a DC generator, it will use the mechanical energy and it will convert that mechanical energy in the form of electrical. So here we are supposed to study about the back EMF concept, because in yesterday's session we have seen how to derive the equations for the EMF in DC motor and DC generator. So what we are saying here, if we are using the DC machine as DC generator, at that time we will get EMF equation as Eg equal to N45 upon 60 into Z by A. We are calling the EMF as a generated EMF because it will work in the same phase with respect to the supply voltage. But when we are using the DC machine that will be working as a DC motor, at that time induced EMF will work in opposite direction with respect to the supply voltage. That's why we are saying that voltage as a back EMF, because that EMF will work in the opposite direction with respect to the supply voltage. Parvez, just wait for a minute. Okay, so what we are saying here, when we are using the DC machines, that will uses the electrical energy and that will convert that energy into mechanical. At that time, we are saying that machine as a DC motor. So here we are supposed to study about the back EMF which we will get in the motor. When there is a current carrying conductor which will be placed in magnetic field, at that time we are saying in the torque will get produced. Parvez, please mute yourself, don't disturb the class. So what we are supposed to see here, we are saying if conductor will cut the magnetic field, at that time EMF will get introduced according to the Faraday's law. So here we are deriving the directions of induced EMF according to the Fleming right hand rule. So what it is saying, it is seen that here the direction of induced EMF will be in opposite direction with respect to the applied voltage. Therefore, we are calling that EMF as the back EMF. If you see that EMF will work, how that will work in series with the applied voltage, but only it is having the opposite direction with respect to the given voltage. So here we can say when we are using the DC motor, at that time you will get back EMF because that EMF will work in the opposite direction. So here what we are saying, when we are supposed to study about the back EMF, at that time when conductor will cut the magnetic field, at that time according to the electromagnetic induction or according to the Faraday's law, he states that when conductor will cut by the magnetic field, at that time EMF will get introduced. So यहाँ पे EMF generate हो रहा है, but that EMF will work in the opposite direction with respect to the supply voltage. And how we are deriving the directions? We are determining the directions of the back EMF according to the Fleming right hand rule. So what Fleming right hand rule states that Fleming right hand rule tell us the direction of induced EMF when there is a conductor which will attach to the circuit and it will move in the magnetic field. At that time it will decide how will be the directions of the current in the generator winding. So here if you see, when we are supposed to study about the direction of induced EMF, at that time we are using the Fleming right hand rule. So Fleming right hand rule states that when we are putting our thumb after that first finger and the second finger, or we can say thumb, index finger and the middle finger, these are perpendicular with each other. मतलब thumb के बाद जो first finger है, it will be perpendicular with that thumb. After our second finger, which will again perpendicular with the first finger, because we are using here Fleming right hand rule, so we can use our right hand. You can practice there, you can do practice here only. How you can take your right hand, how you will take, if you are taking your thumb in the upward direction, at that time your first finger will become perpendicular to the thumb. It will be towards the screen. तुम जो स्क्रीन में अभी देख रहे हो वहां पे उस साइड में तुम्हारा फर्स्ट फिंगर आएगा. At that time, if you are again putting second finger, that will be perpendicular with your first finger. At that time, here we are making three fingers, thumb, index and the middle finger mutually perpendicular with each other. At that time, thumb will decide the direction of motion of conductor, which will relate it with the magnetic field. It means what? How your conductor will rotate, it will decide that direction, your thumb. After that, we are putting our first finger perpendicular with thumb. So the first finger is pointed in the direction of magnetic field. So if you are putting your thumb in upward direction and you are putting your first finger perpendicular with thumb, it will be towards screen. At that time, that finger will decide the direction of magnetic field. And when there is a concept of magnetic field, it will have two poles, north and south. So it will decide that direction. At that time, your middle finger, or we can say the second finger, it will represent the direction of induced EMF, or it will represent the direction of generated current. So here we can say this law, Fleming right hand rule, states that when we are putting thumb, index finger and the middle finger perpendicular with each other, at that time when your thumb will indicate the direction of motion of conductor, first finger will indicate the direction of magnetic field. At that time, your second finger will determine the direction of induced or the generated current. So here we are saying there is a need of back EMF in the DC motor. So back EMF, what is representing? It will represent the portion of the supply voltage which multiplied by the current equals the mechanical work produced. And the rest of supply voltage is used as IR drop, and it will produces the heat. It will dissipate the power. It is wasted the energy. So you really want back EMF which will be very close to the supply voltage, so we can do the mechanical work. So the back EMF, what is it is doing? It is playing the self-regulating role by limiting the current and energy flow through the motor. In parallel motor, it is only due to the back EMF that if you apply good voltage source to the armature with the very low resistance, whether there will be load or no load, at that time you are supposed to run your motor very nicely. So there will be the need of back EMF which will play self-regulating role by limiting the current. So here if you see our DC motor, this is nothing but we are giving here resistance that will be in series with DC motor. So here we are, in order to understand the significance of back EMF, if you see here, we are supposed to derive the value of power. How much power will get dissipated? For power, we will having the equation P equal to V into I. But if we are having the value of supply voltage, we are having the value of resistance, we can derive the value of current. How? According to the Ohm's law. I equal to E by R. So you will get given voltage 12 volt. If they have given, we are taking the example. There is no issue why we are taking, because they have given. So if we solve according to Ohm's law, E by R, you will get 12 by 0.1, that will be 120 ampere. So we can calculate the value of power. We are having the value of I, we are having the value of E. So you can calculate power, and here that whole power value will goes to the power dissipation. It will produces the heat. That will be 1440 watt. So here what we are saying, all the power is going in the form of heat. So there will be no power left to do the mechanical work. So as per energy law, we will require the back EMF. So we can do the mechanical work also. So if you see, when we are using the DC motor at that time, if we are applying here KVL, you will get the equations for E, that is nothing but EB plus IA RA. EB is nothing but the back EMF. IA armature current. RA armature resistance. So here if we are saying resistance of armature is very small. So what will happen if we are taking it is very small? That will be 0 point something, very small. At that time, that value we can neglect. So here if the resistance of armature is small enough, we can take that IR drop very small as compared to the supply voltage, and you can equate supply voltage with the back EMF. For the sake of simplicity, we are neglecting IR drop, so we will get E equal to EB. So what will happen? That is, in practice, the back EMF almost balances the supply voltage because it is becoming very close with respect to the supply voltage. So when motor will start, at that time armature is not moving, so what will happen? EB will become 0. So here the armature current is very high, only limited by small resistance of armature. So you will get initial torque that will be very high, because torque is nothing but it is the quantitative measure of tendency of force to cause the relative motion. So we can take torque equal to F into R into sin theta. F is nothing but the force. R is nothing but the perpendicular distance, the radius of the object which is rotating. And angle is nothing but it is the angle between force and radius, Fr. So here you will get the equation for the torque. How we can say about the torque? Torque acting on a body is a quantitatively defined as it is the product of force acting on the body and the perpendicular distance of the line of action of the force from the axis of rotation. Theta is the angle between that radius and the force. So you will get torque equal to F into R into the sine theta. So we are taking torque is the tendency of force to cause the motion. But what we are saying here, when we will start the motor, if armature is not moving, we will get the value of back EMF will be 0. So here the armature current will become very high, only limited by small resistance of armature. So we can take initial torque as high. When we are applying the KVL, we will get the equation for the EMF equal to EB plus IA RE. You can rewrite that equation, reconvert, rearrange in the form of EB. So your equation will become EB equal to E minus IA RE. So here we can see as the back EMF will will increase. What will happen? If it will increase, you can see here, here is the negative side. So here we can say if back EMF will grow, at that time current will decrease, current drop. So the torque will reduces. Initially we are taking torque is high, but as the value of back EMF will go, current का value कम हो रहा है, that's why torque will also reduces, and it all settles at the point when we will get the torque that will be equal to the load. Here we are decreasing the value of torque to the reasonable value. So here for a reasonable load and the small armature resistance, we are taking the back EMF which will be nearly equal to the supply voltage. So here we are supposed to study about the torque equation in today's session. What we are saying about the torque? Torque is nothing but it is the quantitative measure of the tendency of a force to cause a rotational motion. So we can define torque as it is the product of force acting on a body and the perpendicular distance of the line of action of the force from the axis of rotation. So you will get tau equal to F into R into sine theta. Here, theta is nothing but it is the angle between radius and the force. So you will get this equation. If you see its front view for the DC motor, you will get conductor experience a force and the conductor lie near the surface of the rotor, which will have common radius from its center because it is rotating continuously. Hence, torque is produced where? At the circumference, because they are taking the same radius. So hence torque is produced at the circumference of the rotor, and rotor will starts to rotate. So here what we are saying, when we are using the DC machine, which if it is loaded either as a motor or a generator, rotor conductor carry current. This conductor will lie in the magnetic field of the air gap. So here, each conductor will experience the force due to which the conductor lie near the surface of motor at a common radius from its center. It will be on the circumference of the rotor. How will we calculate? We can calculate the torque value which will be produced around the circumference of rotor. So when machine will operate as a generator, at that time this torque is equal and opposite to the provided by the prime mover. So when machine is operating as a motor, at that time we can take torque which will transfer to the shaft of rotor and which will drive the mechanical. So we can say that torque as an electromagnetic torque, because when we are putting the current carrying conductor in the magnetic field, that will exert the force and it will exert turning moment of torque. We will take tau equal to F into R into sine theta. So we can say this torque as produced due to the magnetic field effect. We can call that torque as the electromagnetic torque. So we are saying the torque is produced in the armature. It is not fully used at the shaft for doing the useful work. But some of part get lost during the mechanical loss, and that torque is used for doing useful work. We can say that torque as the shaft torque, which we are taking to do mechanical work. So here, to establish the torque equation, let us consider the basic circuit of the DC motor. If you are taking the circuit, we are having the equation for the back EMF will be EB equal to E minus IA RA. Or you can write, when you are applying KVL, you can write E equal to EB plus IA RA. So here we will get IA, if you are multiplying both sides by using the IA, you will get IAE, IAEB, IA square RA. So here we are aware about the mechanical power. Mechanical power is nothing but it is, if we see here, we can take mechanical power equal to IA into EB. We can take this power. But here, this is the armature current, this is the armature resistance. So that power we can call as the power loss, or we can say it is the copper loss in the armature conductor. So here we are taking this as the power loss, and this power we are taking as a mechanical or electrical power, which is the input to the armature. So here we can take PM equal to IAEB. This is nothing but the mechanical power. Here, but we are aware about the mechanical power that rotates the armature can be given in terms of torque and in terms of angular speed. That will be measured in the second. So you can take 2 pi n small n t. So here now we can equate these two equations, the fourth and fifth, because both are having the mechanical power equation. So your equation will become IAEB equal to 2 pi n t. Now you can rearrange that equation to derive the value for t. T is nothing but the time. So your equation will become t equal to EBIA 2 pi n. But we are having the equation for back EMF, that is nothing but EB equal to NP5 upon 60 into Z by A. The capital N. We are supposed to write here small n. So you can convert NCO. How we can convert? We are aware about small n and capital N. If we are having the n, you can write 60 into small n. Nishigandha, please mute yourself. So what we are saying here, when we are supposed to study about the torque equation, we are using the DC machine. At that time, we are taking the DC motor, we are taking one resistance that will be in series with that DC motor. So when we are applying the KVL, you will get the equations E equal to EB plus IA RA. But when we are multiplying both sides of this equation with IA, you will get this equation. EA, EB, IA, you can call this as a mechanical power. IA square RA, you can call this as a power loss or the armature power loss, copper loss. So here we can equate the mechanical power equation with the mechanical power, where we will get the equation in the form of torque and angular velocity. You will get mechanical power equal to W into capital T. So you can write that as 2 pi n T. So here if you are equating these equations, you will get IAEB equal to 2 pi n T. But we are aware about the back EMF equations. We are getting NP phi upon 60 into Z by A. That is the capital N. Here we are having small n. So you can take that capital N in the form of small n. How? Small n into 60. You can write. So here when you are writing EB equal to 60 into small n P phi 60 Z by A, you will get the EMF equations, back EMF. So here again we are having the equation torque, that is nothing but EB IA 2 pi n. So I can write the EB value here. If you are writing, you will get this equations. Now what we can do? Again 1 pi 2 pi. 1 upon 2 pi. If you solve, you will get the value 0.1529. So you can write this value here. If you are supposed to write that. Otherwise, you can use this equation directly. But here, we are aware about the construction of DC motor. We can take number of pole, number of conductor per parallel path Z by A as a constant term. So if you are taking ZP 2 pi A as a constant term, K, ZP upon 2 pi, your equation will become T equal to K is nothing but the constant term, this equation, into phi IA. It means what? Here you will understand the value of torque will depend on the armature current and it will depend on the induced magnetic fluxes. So here you will get the torque equations that will be equal to K phi IA. This equation you will be needed to solve numerical. This equation you will be needed to solve numericals. Also you will be needed this T equal to phi ZP IA 2 pi A. We are taking K is nothing but the constant term ZP upon 2 pi A. These equations you will be needed. So from these equations we can say torque produced in armature is directly proportional to the flux per pole and it will be directly proportional with the armature current. So here the direction of electromagnetic torque developed in the armature depends upon the current in armature conductor. If either of two is reversed, torque will also reverse. But if we are reversing both magnetic flux and you are reversing the armature current, there will be no change in the torque because we can see here torque is depend on both flux and armature current. इसमें से एक वैल्यू चेंज हो रही है, रिवर्स हो रही है, तो टॉर्क रिवर्स होगा. But if you are reversing the both magnetic flux direction and the armature direction, armature current, that time torque will not get changed. Here we have finished about the torque equations which we are supposed to derive for DC motor and the DC generator. If anyone is facing any issue, you can ask.